Hello guys. Uh, Today we are going to talk about the Reynolds Transport Theorem, and I hope we could finish the chapter 4, and then next week we'll start chapter 5. Why? Because for Wednesday I will have a review class for chapter 1 to 3 plus 7 that are going to be in your exam. Exam is on Friday. It's 2.5 hours plus maybe 15 minutes additional time for submission. So you have to manage your time to have at least 2.5 hours, but a little more, maybe 3 hours free to be in the exam. Uh, we'll talk about the questions and how would be the exams, this question distribution from chapters. 31 question from each chapter you will have, but we have a bunch of the small questions, so 4 small questions plus 4 long questions, that totally 8. Then I have to still work on it to see how it would be, but yeah, something close to that. So let's talk about the control volume and system representations that give us the meaning behind the Reynolds Transport Theorem. So as you may know, when we are going to study the fluid that is in the moving, it's moving or it's at rest, we need to sketch a control volume or boundaries that define where we are going to do the study, right? And this is very important that you, because this is going to give you the boundaries that give you the area of surface that the flow comes in, goes out, or where part of the fluid is the part that you are doing a study on. And still is very important because the mass, the density, temperature are inside of that. It may different with the outside. Some of the properties like mass, it depends to the amount of fluid and size of control volume or system that you consider. And some of those are not, like temperature. As long as the temperature in the whole control volume is constant, then it doesn't matter that how much space in the domain or in a space you consider for the control volume. So we have two concepts that are used to describe a fluid flow. One of those is system, and the other one is control volume. So the system is based on Lagrangian approach, and control volume is based on Euler approach. What these two are different, and how these are related to Lagrangian and Euler approach. At first, the system is a collection of matter or fixed mass with fixed identity. For example, if you see here, that's a car piston. You can see the gas or fluid or anything that is inside of that with the atoms that are rotated here, fluid particle or molecules or atoms, they are numbered here. So these are identities of these molecules, right? If the system size change, means that the piston comes down and then goes up, the system is closed, the boundaries are closed. What does it mean? It means that these are not changing. The identities are fixed. So the same mass and the same identity of the fluid particles are still here. So it's very important because the system is closed. So the boundaries, as you see, the boundaries, when the state of the system, the state of the fluid changes, the boundaries are moving. Why? Because the fluid particles are moving and you want to move your boundaries to keep those fluid particles inside of the system, right? So because you want to be unique in the identities, you don't want to switch between one particle or another particle, right? Like a group of people that are coming to visit you. right? And you are moving with them, those people, and showing the UV to them. So what will happen if some of those going somewhere else? So you will go in there and ask them to come back, or you will understand that these are people that I'm responsible for them, right? So you want to keep those. So it doesn't matter where they are going, you want to consider your attention to those people, not the how they are then standing, they are sitting, or they are far from each other, right? So these are the people. So that's why the boundaries are not fixed. And also, you can understand that these boundaries are like a rigid wall, like a real walls. So like a room. And they are moving, but they are fixed. So the boundaries from inside of that wall, no one, nothing like particles going out or coming in. These are closed. So the mass is fixed, the identity are fixed, and system is closed, right? But what about the control volume? The control volume, you will consider an imaginary wall in the space that is fixed. Okay, so you don't care that where is the fluid particles and from where is they are coming and which of those are coming and going out. You will fix your control volume in space, and you wait here and see that how the fluid comes in and goes out. So exactly, you have the same room, you have the same boundaries, but the if you capture the identity of the particle, they will change because the fluid that comes in time is going to change, but the flow is moving. So these are like imaginary boundaries or imaginary walls. So you have the wall, but they are not real wall because the fluid going past through it. Okay. So why this is a Lagrangian approach? Because Lagrangian is tracking particles. So it matters that which particle is tracking and consider those identities. We care about the identity of the particles. That's why this is like a Lagrangian approach, and it moves with the fluid, right? But the control volume is Eulerian approach. You will stay somewhere and just track the particles. So you have a like a conference, you have a paper, you're standing there, and people are coming and see your paper, and you explain that, but you don't follow people. So you're standing in fixed point in the space and wait for particles to see, wait for visitors to come and see your paper. And when they are going, you don't care that which one is came, you have to be responsible to explain it. And when he or she left, you will wait for the next one, right? You don't care that, hey, your identity matters, I'm going to follow you. No, you're fixed in space. That's the difference between control volume and system, or Lagrangian and Eulerian approach, right? So the thing is that we need Reynolds Transport Theorem is a relation between these two. That this relation is Reynolds Transport Theorem that wants to see that how these two systems are connected, right? Because these two are different. In one case, you have to move with the boundaries are moving because the flow is moving and you want to be fixed with the identities. So the same boundaries at the time zero or this control volume or control surface are matched. But when the flow moves, your control volume is staying here because it has to be fixed in the space, but the boundaries of your system are moving with the fluid because they want to track this fluid. And these particles that are here are moving in this side, so your boundaries are going to move. And also these are going out. So the other boundaries should be going out and change to here because it wants to keep that identity of those particles, of the same particles inside of it, right? Same as here. So the Reynolds Transport Theorem is going to find a relation between these two, that from that we're using to find the governing laws of motion, actually. Because the governing, in the fluid, we have two concepts. One is the flow behavior and a governing equation, or like a streamlines that are for uh, fluid. And also we have particles. So most of the time, if you have an unsteady flow, it's possible that you have if you track particles, you will have a different streamline or path line for that particle compared with the real streamline of the flow, because the particles are free to move, right? If you see that in general form, that is unsteady. So they are moving inside of each other, and you know that these are different with the flow streamlines. So, but you need to know the particles path line, because from that you can find on average find the streamlines. So that's why we need Reynolds Transport Theorem to make a connection between these two, and from understanding of that, finding the governing laws of fluid motion. Fluid motion and fluid particles motion are different. And also you can shift from the system analysis to control volume analysis, right? Okay. So when we are saying that we are moving from system analysis, means that Lagrangian approach to Eulerian approach. Okay. So how we can do it? As at first, if you come back here and check it, this one. If you see here, it is in this one, mass is fixed, right? Mass is something that is related to the amount of fluid particles, right? Because the fluid particles give you the number of molecules, because each of those are a pack of molecules, and you count those molecules and sum up the weight of or mass of the molecules, and then sum up all, you will have mass of your system, right? Since that's fixed, you don't care, because you don't care the mass. Mass is going to be a constant. But here, based on the flow velocity, and since the flow has a velocity, maybe the pressure, static pressure changing, the temperature changing, and then you are fixing the boundaries, it is possible that you have different number of particles here, right? So you have mass is different. So those parameters that are related to the amount of particles are different in system versus the control volume. Why? Because in system, since the mass is constant, those parameters in the fluid that are changing with the mass or amount of fluid are not changing anymore, because the mass is fixed. But in the control volume will change, right? So you have to first make a connection between the parameters. At first, you have to know that how I can find a definition of the quantity as a specific quantity, that amount of that are not related to the mass. So if I say that B is a quantity or parameter in fluid, it could be any parameter like mass, velocity, acceleration, even momentum, temperature, and so on and so forth. It could be any parameter, right? Some of those may be such as temperature, if you have a uniform distribution or homogeneous distribution, and you don't have any heater or something that make your fluid cool. So the temperature would be constant, right? Doesn't matter how much of the fluid you have. But for all is working, because then if you multiply the mass on it, nothing gonna change. Doesn't change anything. But you can say that I have two parameters here, mass times the specific quantity. The specific quantity is defined as amount of B, capital letter P, per unit mass. Okay, so that's how we can define two parameters, type of parameters or characteristic in a fluid. One is capital B and lowercase b. The capital letter B is extensive parameter, and this is intensive property or parameter. So extensive parameter is directly proportional to the amount of mass. And the value of intensive parameter, the value of intensive parameter or property is independent of mass. That's the difference between these two, okay? So if I consider that relation between these two, like capital B and lowercase b, or the extensive and intensive property, then if I multiply by m, that m is in a fluid is rho times volume, then I can write the capital letter B, or in extensive form is rho v b. Okay, but again, in a fluid, you're talking about the fluid particles, right? Because the parameter may change from particle to another particle. So that's why we're always talking about the very small amount of volume. That's why we need integral for and rho b dv. That dv goes to almost 0. Okay, it has to be very simple. Based on these assumptions, now you can connect these two system and control volume, and then find a relation between these two, which is your Reynolds transport theorem. First, let's say you have a flow at time 0, right? So this is the flow at time 0. And this is your boundaries. And I will write that this is your system boundaries. Okay, so this is our system boundaries, and these are fixed because the flow is at time 0. Let's say that time is freezing now. So the free particle are standing here, and like you freeze it. Now if you play that, the flow is going to move with velocity 1 coming in, and so velocity 2 here, and it's going to move. But the boundaries of the system also moves, right? It's obviously based on the assumption it should move. At time 0, it's very important to know that the control volume and system boundaries and control volume boundaries, which is your control surface, are totally fixed and match. So B of the system means that how much amount of the, like, just assume that B is like mass, okay? Just assume that B is mass, because it could be any parameter, but it's better to understand it with mass, right? We can assume anything like this. So if that's mass of this system is the same as mass of the volume. At time t, you freeze the time. So I can write that P of control volume at time t are equal to P of the system at time t. Okay? But what will happen when it moves? When it moves, absolutely, this is your system because it's moved with the fluid, right? It moves and it has to move boundary because the system should be keep the same particles. A particles are moving, it has to be there, right? But this system had a boundaries here at time t, if I bring it down, right? Why I need that to compare with the previous one? Because that is your control volume as well, right? So also I have the boundaries here that is moved. So it moves forward. So if I bring these two on top of each other, then I have a overlapping area. I have, that could be 3D, doesn't matter. Again, going to be control volume. Absolutely in general is a volume, but that's easier to show. So I have overlapping area, and also I have a part that is here, and we put it 2, and we name it 1. Okay, and we have a part of here. So as I told you before, this is your system at time t, and your system at time t is your control volume. So these are the control volume boundaries, right? I can say that this is the control volume boundaries at time t, but at time t, at time t plus t delta t, at any time, control volume boundaries are fixed because you have to be fixed in space. Nothing gonna change. This is not going to be changed by the flowing move, when the flow moves, or the time change, because control volume is fixed. So these are the control volumes boundaries. And if I overlap these two in this system, that the system changes in a delta t time, what is the relation between these two? This is my, from here to here is my new system, right? So the B of the system at t plus delta t. Perfect. So I know that this is part of, okay? And that's not in the system now, but it was in the, it is in the control volume, okay? So if I consider that these are my control volume at time t plus delta t, which is the same as control volume at time t, then this part is going to be P of control volume, because that's from here to here, the control volume at time t plus delta t, which is again the same as t, minus B of the I. Why? It's like area of the gray one, right? So the control volumes at time t plus delta t minus Bi is going to be the area of the gray in the figure, okay? And also this is B2. So from here to here, you have a system. What would be the area of these two? Area of the summation of these two areas going to be your system at time t plus delta t. So B of the system at t plus delta t is B of the control volume at time t plus delta t which is here minus bi plus b2 here. So you find the connection between these two by considering that the fluid in a simple shape with the assumption that yes, fluid is 1D moving in one direction, but the volume is 3D again. And you find a relation between these two, okay? Till now, you connected two system of processing, which is the system analysis and control analysis just based on the amount of fluid. Why? Because the amount of fluid is your B, and the rate change of that amount of fluid, and B going to be any parameter. So if you find the rate of change, or for example, velocity, if you consider the verb B is velocity, you can find the rate of change with these two at time by increment time, which is delta t. So if you find B in system analysis by the rate change of that, time rate change of that, then you can find also rate change of that by control volume and then connect these two. What when you have the velocity, I consider B is velocity, then you have a time rate change of velocity, which is your acceleration. And acceleration in the system and control volume are connected. Mass change of system and control volume are related. When all parameters are related in these two approaches, then you can find that because the equation of movement are all based on these parameters. So when you connected these two, then you can connect everything in these two equations, and you find final form of the Reynolds Transport Theorem. For now, I will put a I here, or 1 and 2 here. These are your two questions. And also, I will write a time here. The BI and B2 are at time t plus delta t. Okay. In the control volume, which was from here to here, BI also can be seen as the amount of fluid that comes inside of that. Let's say that this is your control volume like this, okay? Your control volume, which is fixed. Then the flow moves. This part of fluid particles are coming in and these are going out. So that's why we can say that BI is your B in, again at time t plus delta t, and B2 is your B of out. This is also could be written instead of 1 and 2, you can write that yes, it's coming in and going out. So B in and out. Okay, perfect. So what else we can find in this? The other thing is, the final thing that we need is finding the rate change, right? The time rate, the rate change of the based on the time for that parameter. When it's at the system or and then replace with the control volume, then we connected these two, right? So in the equation 3, we have, you can write that the delta B of rho D over rho T, which is delta B of the system over delta T. And if you check it out here that we wrote here, is going to be finding the rate is B system at T minus T plus delta T minus B system at T over delta T. Exactly is written here. Delta B of system over delta T is B system at time T plus delta T minus B of system at T over delta T. So this is your equation 2. And this is our equation 1. If we want to replace, then what we have to replace? Equation 2 and equation 1. Right? Equation 2 and equation 1 are here. And what is the meaning of this term? Is a change in the amount of V in the system in the time interval of delta t. Okay, that's simple. Okay, so I have a question for you. Can you find the that's like a derivation, like finding the limit of that, and delta t goes to 0. Can you find the answer for that? For now, it's not possible. Why? Because system is constant in space. Oh, the amount of that parameter at time t and t plus delta t are constant, right? So these are constant, and you can write that the b of t plus delta t is equal to b of system at time t. Then the summation of these two, or this one minus b system at t, is going to be 0. Delta t is going to 0, then the answer of that is 0 over 0, that you cannot find for answer for that, okay? Because the b of that system is always constant over time, okay? You cannot say that because your assumption for assuming the boundaries are there, okay? So the way to get this in limit is replacing these two with the equation 1 and 2. So if you replace with equation 2 first, then you can say that b of control volume at t plus delta t is equation 2 plus b out, which was b2 of that system that we showed previously in the previous part, and b in is b1, right? And also we can write that, okay, b of system at time t is also b control volume at time t. These two are matched, and just bring delta t behind in denominator of that as well. Okay, perfect. So if I combine these two and bring b out and b in out of the this term, then b out minus b in over delta t is equal to time rate change of parameter b, or property of b, in control volume. So what is related now? It was the change in the amount of b in the system, in the time interval of delta t. Now is connected to the change in the amount of b in the control volume in delta t interval, right? That's why these two are connected to each other, okay? So I can write that here as well, that this is going to be your b dot of control volume based on this, if you get the limit, then plus b dot of out minus b dot out of in. And also I have to give you a hint about that. When you get in the Lagrangian form, that's a thing in the fluid books, that in Lagrangian form, if you get a time derivative, then it has to be shown by capital D over dt, which is our total derivative, right? Is thing that we talked about that before in chapter, in the early in this chapter. So the capital D is for Lagrangian form, and the rho that we use, or the lowercase d, is for Eulerian approach, or local rate, right? You have two terms, convective, we had two terms, convective one and the local one. So The local is going to show by a round, but the capital is for Lagrangian. That's why we use capital form D here, because the system is for Lagrangian system, is Lagrangian approach. So the derivative, time derivative change of that is going to show by capital B, right? So now here we connected control volume and system to each other, but it still needs to be changed. So how? By replacing the B with the equation that we define for the property. So any property is equal to B, which is intensive form of that, multiplied by rho density times your small volume or particle volume, okay? So if I replace B out or B in, if I just replace for now B in here and get the limit of that, because that's the time, it's a dot on top of it, right? So B dot in is the limit of B in over delta T, and delta T goes to 0. Then I replace B1, rho 1 delta V1 here, right? So what is delta V1 now? Delta V is the volume, right? When the fluid moves, you have a volume change. Okay, so it's going to be your area or cross-section area times delta L1, right? If you check it here, and again, why this is a delta V? Because again, the delta time is delta increment is delta T. So this amount of volume are very small. That's why we can say that this is only delta V, and we get the integral of those, right? But also, what is, if that's delta V, what is the volume of that? It's going to be your L, which is from here to here. Again, it has to be delta L because the time is very small and the velocity is normal, like it cannot be the speed of light. So the delta L that the boundaries are moved are also delta L. But the cross-section area of that is could be any, right? Could be a pi. So it could be considerable. That's why the area times delta L1 is your delta V1. Then now A1 is a constant, but delta L1 over delta T is your V1 or the input velocity, okay? So I can write that here, that in this form, we put the rho here because we don't know that it's incompressible, compressible, and we don't want to have a specific equation here. We want to have a general form. And B1 rho 1, A1, when the area changes, over V1. Delta L1 over delta T is going to be your V1. The same here, B2 rho 2 delta V2 over delta T. That's the volume, not velocity. B2, this is going to be A2 times delta L2. The same as above is going to be rho 2 A2 B2. Okay, perfect. So we have an understanding for B dot in and B dot out. Okay, and if we replace these in the equation 4 that you have here, then you have better view of you can find the derivative changing system, right? Using the control volume, because tracking particle or having a system that giving identity to particles and tracking those is hard, okay? It is a common approach in experimental things and also for just limited number of particles. But again, tracking particles are very hard. But being in a fixed position in the domain and just check the boundaries and the velocity, because you only need the pressure sensor and some of the pressure sensor over the boundaries, then studying the fluid in this method or control volume based or Euler method is much easier, It's less energy, less time, and it's possible. Most of the time, it's not possible in the Lagrangian approach. That's why we need to find all based on the control volume. And why we are connecting system to control volume, because the system is the final answer that we need. Okay, we want to have a definition for the movement of all the particles in the fluid. That's the goal. That's the goal of fluid mechanics. Okay, yeah, if I have thousands of the particles, how they are moving, so I can give you the equation for all of them, right? You only need to give me the the time and the location zero of that particle. Then, with my understanding in or equation of movement, I can give you the path length. The path length for that specific particle, it's huge. So if you understand and you can give me that, then you can say that I know how this fluid moves, right? But it's hard because you have to give me for particle or particle. If you are going to do that, you have to split your space in the different location of the input location and then track those particles and find the equation for that. And then you can say that, okay, I have a different location point of a starting point, then I have the particle. If another particle comes here, this is going to be that way. But since they are moving on inside of each other and they are free to move, then you have very different uh, than control volume. You have hard time to find or study the fluid. But in control volume, it's much easier. You have a fixed space, you have fixed boundaries, easy. You are waiting here, just check it in general form. And with the B out and B in, which is related to your control surface or the boundaries of your surface boundaries or input and output, when the flows comes in and out, you can find with the summation of those can find the derivative or time rate change of the mass inside of the system. Okay. But what is the assumption till now? Because again, Reynolds Transport Theorem should be general. If it's not general, it's not useful. So you want it to be a general form, but still we have restrictions. We consider the control volume is fixed, right? This is the assumption. It's not a restriction or something that jeopardize its generalization form, okay? It's the form that is not useful for the other system control volume, because the control volume always is based on the assumption fixed, right? You only mentioned that is one inlet and one output. So we need to expand it to multiple input and output, like heart. So if you consider your control volume is a heart, it has two inputs, two outputs and two inputs. So this is going to be multiple input and output, but you have still for only one, because we have one input and one output, right? You need to expand it. Also, we found we had the assumption that uniform properties across the inlet and outlet. Uniform properties, not uniform velocity. Uniform properties means that you have a homogeneous form. Again, it could be different, absolutely, but this is the assumption. It's not something that you can change it. And also velocity was normal to the sections, right? So it was normal to the area of 1 and area 2. These two should be expanded. If you expand and get rid of these two restrictions, then you can have a more general form of that, right? So for inlet and outlet, multiple ones, it's easy because you only need to sum up one. So if you have multiple inputs, then B dot of the ins in I, if you sum up all, and also B dot of the outs of I. And if you want sum up all, then you can replace this one here over the out and in with the summation or sigma of those and out with the sigma of those. That's easy. But what will happen if the velocity is not normal? Okay, so we need to take care of that as well. Okay, so again, these sigmas are not working if the velocity are not normal, because this is not that much simple, because the velocity is normal, not normal to area, right? And again, if you come back here, we find the velocity, the b dot in and out based on the volume of that, right? We consider the velocity is normal and it comes in. That's why the cross-section area doesn't matter what is it, it's A1, but when the flow moves in normal direction, then this is going to be delta L. What will happen if you consider that your control volume is here, but the flow passes like this? It's going to be different with that, right? You cannot say that delta L is here. Even if you say that, okay, that's my delta L, how can I find the volume of that? That could be hard. That's why we need to make a general form. Okay. The general form of the Reynolds Transport Theorem, which is RTT, or easiest to show. In general, we consider an arbitrary fixed control volume, okay? That could be control surface. So these are all control surface, as you see here. We'll show it with the C.S. Okay, that's all control surface. So we consider a normal vector, which is normal to our area. Okay, n is the direction of the normal, and always is going to point away or out of the opening. Okay, so it's going always normal to the area and going up. Then also you have a velocity that now you know in the, it's different with your assumption. So it's going to be have an angle to the normal direction. It could be any angle, and also always, it's not always zero. It's not always parallel to the n, okay? So n is the normal to opening, and flow velocity is v. So what we need v of the n, right? What is v of the n? V of the n is the velocity component that is in the direction of the normal direction, right? So what exactly we need is that. If we find that, then everything is easy. We can use again the sigmas and the equation. Only replace that with Vn, okay? But what is hard still is not working, because the area could be changed, because the normal direction is also always changed. Let's say you have a pipe, okay, but the flow is not normal. It's moving with the angle of theta coming in, okay? It's okay, it's coming in, like you have a channel or the pipe and also the blow wings, but the blow is not directly normal to the cross-section area of the pipe. Is with the angle. It's not hard, because you can find the angle, then the velocity of the wind, and you know the normal direction is going to be normal to the area, and find the vector of or component of velocity by multiplying by cosine of this, right? So Vn is also from mathematics is velocity times cosine of that. Okay. But what that's still easy, okay? But what will happen if your cross-section area or input area is like a curve? Then even know that you have a velocity with an angle, right? Even it's not normal, but by changing the curvature or moving over the surface, then is sometimes the angle is also changed, right? So if you have an output or arbitrary input and the velocity is like a wind, then normal to this point is here, but normal to this point is here, the normal is here, right? So you have to split it to very small amount of surface and find an integral form. That's the difference, and that's the general form. Because with the integral form, you can split it to the areas that the angles or the normal direction is changing versus the velocity direction. Just before checking the arbitrary surface, that we split it into the portions of that, let's just finalize this one. Just keep in your mind, if that's our pipe and you have normal direction here and you have a normal direction here, it's always pointing outward or out of the opening. And the velocity here is coming in and the velocity is coming out. Okay. The V dot N, so V and N are normal, are parallel. No worry about the theta. Theta here is 0, and the cosine of theta is 1. So V dot N is going to be V. But in the opening, the angle is minus 180, is 180 or pi. Then the cosine of pi is -1, right? So the V dot N or V of N is minus V here and it's positive V here. So do you have a switch between the signs? And it's a little confusing because we say that why I have to find minus of the V, but the flow comes in. So the property is added to your control volume, but you have to add a negative sign there, right? Because again, you're comparing the system and the volume. The system are moving, so you are checking the system, okay? Not the control volume. You are just connecting these two. So keeping this in your mind, in this way, or understanding this, that if that's or B of the in, it's not actually the property or B that R comes in. Because the system is moving. This is actually something that's going out, not coming in. And the part that is like a fish that's moving and the water comes inside of the mouth, right? So it's going to bite the fluid. So it's going to bring part of the fluid by its movement, okay? So actually this part based on the velocity comes in the control volume. But since we are doing the connection between these two, for this part or the system that are moving, this is going to go out because that's our fish, and fish is moving with the velocity, right? It's moving with the fluid and the system is moving, which means that the parallel velocity or the relative velocity is 0 because these two are moving with each other, right? But when it moves, the particles, new particle or new part comes in and this part goes out. But for the control volume is different because the velocity, if you consider the velocity, flow has the velocity, part of it comes in from this side and goes out from this side. That's why we have Bi as the in, but actually is out. That's why we need a negative sign for that. Okay. So what we can have here, we have an arbitrary shape and we have an arbitrary direction for velocity. Okay, let's say you have a portion here. It's not for a curve, it's actually an arbitrary shape. So if you have a portion, every time that you get the V dot N, if it was negative, then it's going to be your input flow. If it's 0, is net flux is 0. Okay, so this is like a wall. It could be like a wall. Why? Because the net flux is zero and the flow is not passing over that. Why? Because we always normal to the end, and it means that the net flux that passes over the surface is zero. And here you have b dot n positive, means that you have an output flow. So these two are exactly the same shape. The n is here, but the velocity changes. But you have to know that y is our output flow. And how can I say that the system are moving or can sketch it here? Why? Because the normal direction is always outward. So it means that the input is going to be here. This is inside of the system, and that's outside of the system. That's why the n is in this direction. Okay. Now, if we sum up all and find the over the control volume boundaries, means that these are or del ds, right? Because these are a small portion of the area. And this is ds1, ds2, ds3, and then we multiply v dot n by this one, and the second one, the third one, and we may have more and more. Then if we sum up all, we have S of our control surface, and we'll have the sum of all of v dot in and out, right? Both of them at the same time, but getting the integral. That's why we have integral form of that. Okay, so we write that v dot out and v dot in, that we have the negative signs here over the control surface, but the control surface that's going out and the control surface part that comes in. Okay, so surface of the out and surface of the in, because you have a we are to taking care of the control, the negative sign, right? We have v dot out, v dot in. But you know that here you have a negative sign, and you know that if that's input, then the sign inside of v dot n is negative, right? So you have a negative sign behind of that here, and you have a negative sign inside of that, which is hidden here, right? Because we have shown that this comes from the cosine of theta, right? So if you multiply negative sign in this negative sign, then you have a positive, and you can say that yes, sum of all for the whole control surface, then you have a general form that is over the control surface. That's all you have to do. You don't need to be worried about the input and output points, and you just check it portion by portion that where is the input and output. You will say that, okay, for any portion, I will just need the normal direction or v dot n and the component of velocity and multiply by the rho, the intensive form of the property multiplied by area and over the control surface. It could be a sphere, it could be pipe, and for pipe also is the same. So for pipe, you have area here, you have area around this cylinder, and you have area here, right? What is the control volume for you? The control volume is the whole, this pipe. Yes, absolutely. The walls has to be considered, right? But you know that the velocity here, not only that because of no slip boundary condition is zero, but it's always parallel to the surface, right? It's not passing over the wall. It's not possible to pass. And also by mathematics, the velocity is normal, parallel to the surface, and normal direction is always this way, okay? Or it's outward. Doesn't matter because it's the angle between these two are 90 degrees, and the cosine of that is going to be zero. So the control volume that you have is the whole your pipe, and the control surface again is the whole boundary of that. Okay, but since we know that these are rigid walls, and we know that flow is not passing over them, and also we know the velocity is zero at the wall of the pipe, then we can only check that these two openings. But we are doing that based on the experience that we know what is the, because pre-assumptions that we have. But if you are still doing that in the whole volume, I'm telling you because you have sometimes a shape or a case that you even cannot say that from where to where in this surface the flow goes in or goes out. Even you cannot just prejudge it. Yes, we have a bunch of that complex shapes, okay? And finally, the control volume of the B of the control volume is same as the consideration that we have here, is the summation of all intensive parameters, right? So finding the B of the control volume is different from here. Yes, V dot in the dA is over the surface, and that's over the control volume. Okay, so it's over the volume. So what does it mean in general? It means in general that you have a time rate change of the parameter in T, okay, which is for the system, changing of that parameter in the system. You will get the time rate change of that parameter inside of the volume. Why? What does it mean? It means that, for example, you have a fire or you have a combustion. So part of the mass is going to be used, right? It could be changed inside the control volume or the flows. This is different with the flows comes in and out. So if you have a control volume fixed, and let's say that you have a mass, okay? If it's the control volume fixed and you don't know, you don't right now, you say that the summation of the flux, net flux over the boundaries are 0, then what would be the rho of rho T of the mass property? So mass property means that B is mass, okay? So that lowercase b intensive form is going to be capital B over rho over M, right? Because capital B is your mass, then B is going to be 1. This B is 1. What would be the integral? Integral going to be control volume times rho times delta V. Is going to be your mass of your system, right? So the mass of system is not changing. The absolute is going to be 0, okay? But if you have a combustion and also flows that comes in, let's say you have an engine, like the engine that we showed at the first, you have an engine like, here. You have an engine here, okay? So the air is coming in, and also let's say you have a combustion here, which is not, this is not the whole shape. But let's say you have a combustion here, and the flow also part of the exhaust system. In exhaust system, part of the smokes are going out, okay? So in this control volume, you have a mass from the flow, okay? And you have input and output. You will get the rate change of the mass by getting by summation of the input and output, the amount of fluid that comes in and goes out. Okay, perfect. You have this integral. Okay, but still you have to ask this question: if the mass is conserved, conservation of mass is obviously there. But if you have combustion, then part of the mass is going to change by time because of the combustion and fire, okay? Then you can also have a different amount for this integral, right? Over the control volume also may change. So we have two types of change in any parameter inside of the control system or control volume, or control system in general, that if you have a fixed control volume, okay, part of the fluid could come in, then add that property to your system. Part of the fluid is going out, okay, so it's going to decrease amount of that property, and also in time that property may change. Okay, it's hard for considering the mass because mass is conserved, But what about momentum? If the flows comes with a higher velocity and goes out with a lower velocity, and also because of the shapes that you have inside of the control volume, or because of the vortex of the flow or circulation of the flow, then the momentum also change, right? So you have three things. The flow comes in with different velocity, goes out with the lower velocity. Then you have a add up the momentum inside of your control volume. And also because of the vortex that you have or circulation of the flow that you have, the velocity may change, right? Near the walls could change, or maybe you have a fixed shape here inside of that. Like you have a control volume, but you have a shape inside of that that change the velocities here, here, and here. Then momentum also change over time, okay? These are make your system complex, but your control volume inside of that, by time, that property like momentum changes. And also plus of that, you have part of the velocity different that from comes in and out. So the come in flow has a higher velocity, which is your jet velocity. But when it goes out, it has a lower velocity. Almost, it wants to, you want actually in the engine of an airplane engine, you want to use that compressor actually. If you don't know what's that, it's a compressor. It's get the flow, and you have blades here, and you can see it's with the green. These are blades. The flow pass over the blade and pass over these different sizes of that and get the velocity or momentum of that, decrease the momentum and make it almost to the very lower momentum by decreasing the velocity and increasing the mass or compressing that. Okay, by compressing that, you have but higher quality, because after that you will have a combustion channel and a chamber. Actually, it's a combustion chamber, and then you have another. So you will get the velocity or momentum of that inside of a control volume, then add uh, the gas on it and make it fire. This is your chamber. And you increase the temperature and pressure. And from this temperature and pressure inside of the turbine or maybe nozzle, you will get the velocity of that, okay? And you will have a huge, hot and fast velocity in the output or exhaust system that gives you the thrust over the airplane, okay? That's whole thing. But why this figure is shows down there? Because not only the velocities comes in with different velocity that goes out, then momentum, for example, change by getting the average or getting the summation over the boundaries of that control volume, right? But also inside of that, you will have a shape that suck up your boundaries, your momentum, and the momentum is going to decrease by time change. So I guess that you will have now you will have the Reynolds Transport Theorem and relation between the system and the control volume. So that's the end of our chapter 4. I may just give you this week off for reading the course and be ready for the exam. Next week, Wednesday, you will have the homework for this chapter, and a week after that, you have to submit it. So you can wait till that time and review this chapter and submit your homework. But I guess that's enough for today. Any question? If you don't have any question, you can leave. Have a good day, guys.